We just wrapped up Chapter 5, Computing Components, and that's in the hardware layer. Moving over to the programming layer with this lab in the low-level programming languages and pseudocode in Chapter 6. So we're moving from hardware layer to programming layer, but you're going to see a lot of similarities between Chapters 5 and Chapter 6. And that is because low-level programming is tied to the hardware that we were examining in Chapter 5. So there are two general types of programming languages, high level and low level. After von Neumann had his aha with the stored program concept, that programs did not have to be directly wired from circuit to circuit, but that binary zeros and ones can be used to store a program just like zeros and ones are used to store data. So after that aha, the next way to program was called machine code, and that was literally the zeros and ones that the machine executes. This is the lowest level programming language. It's the language built into the machine, and then you will see that a decision was made. You know what? We can create a mnemonic, a little code for these zeros and ones, and thus came assembly language. But assembly language is just machine language with a code for the zeros and ones. The textbook looks at a virtual computer called the PEP-8. It is a very simple CPU, though for us, just learning this material, it seems very complex. Here is what the CPU will contain for registers. So the PEP-8 contains the accumulator. You may remember from Chapter 5, the accumulator is the running total. It's the running sum. It's the result of an operation. It's the answer. For example, if you have a handheld calculator and you see the answer, and let's say you have 54 stored as an answer, and then you add 5, you will see 59. That display on the calculator is similar to what an accumulator is doing. It's holding the running sum or the running result. Next, we have the program counter. Now, the program counter is just a pointer to where in RAM is the next instruction. Each of these is 16 bits. Then the PEP-8 has a 24-bit instruction register. The first 8 bits hold the instruction. The next 16 bits holds the operand or the data that you want to do the instruction with. Then we have memory, and it looks like we have 65,000 bytes. Let's look into a little more detail into that instruction register, which had the 8-bit instruction and the 16-bit operand. So the 8-bit instruction is divided into 3 parts. The first 4 parts will always hold the instruction, the codes, the zeros and ones that mean add or store. This 5th bit is a register specifier or a 5th bit of an opcode. So if an opcode does need 1 extra bit, it can come over and use that bit. The final 3 bits are the addressing mode. We will only use 2 addressing modes in the PEP-8 and in this lab. Here we have the 2 options for the addressing mode. If you only have 2 options, you really only need 1 bit, but this computer uses 3 bits. So 000 means you're going to find the data for this instruction right here in that 16 bits that follow. It's called immediate addressing mode. Yep, here's the data. It's immediately following me. If 001 is in the address, 3 bits of the address, then the operand that follows is a pointer to where in RAM it could grab the data. So this reference says, go to this address in RAM and grab the data. That does slow up the instruction a bit when you've got to access the data in RAM. Okay, so here are our instructions that you can put in the first 4 bits. And you notice that character input and character output for this requires 5 bits. Okay, so 1100 means take the data and load it into the accumulator. So we have 1100, and we have immediate addressing. So this means 7 will be loaded into the accumulator. almost the exact same command here, but now we have 001 is the address mode. So the operand specifier is saying go to byte 31 in RAM, and you need to load that into the accumulator. Again, 1100 means load into the accumulator. The address mode just says where are you going to get the data to load into the accumulator. So pages 159 through 161 steps through all of those opcodes, or all the instructions that the PEP8 understands. Here is the sample program that I'm asking you to take a look at for assignment 4. This sample program writes hello. I want your sample program to write hello world. You have the first 6 instructions already written for you, but when you make a modification, that stop is going to be pushed down. So after the O, you will be adding the instructions to print a space in the word world. So here is the software that you're going to be using for the lab, and it's a simulator called the Super Simple CPU. It is even simpler than the PEP8 that's demoed in the book, and the instructions are different too. So the opcodes do not match what's in the book. But you notice we only have 16 locations in RAM. Each location is 16 bits, I believe. We have this simulates input. You will actually be able to input some binary data here and output data. Now, you will see here that computers can do complex things, but ultimately, each instruction is very, very simple. So what makes it powerful is the ability to do billions of instructions every second. Inside the CPU, we have 4 registers. We have the program counter. Again, this is going to point to where the instruction is going to be. We have the accumulator. We have a temp register, temporary, hold some data, and we have the instruction register. This is the instruction that's going to be executed. And notice that we also have some data buses. Down here we have help. So if you need some additional instructions, we have a help button here. And we have an opcode list. And we have an opcode list, and that opcode list may be handy reference for you as you're trying to decipher what's going on with our instruction. In the lab itself, in the instructions, if you need a little bit more information about each of these opcodes, you will see more detailed instructions. So notice that each of the opcodes are exactly 4 bits, and the remaining 12 bits in each memory address will contain the operand. Let's go ahead and take a look at one example. So you notice that right now the program counter is all zeros, and that's a 0. So we're pointing to the first instruction in the program. If we take a look at the instruction 0100, what is that? Well, 0100 means load immediate. So you will see then the next 12 bits contains a 101 at the end, which is a 5. So what this should do is simply load 5 into the accumulator. I will do a 1-step, and you will see that the program counter is referencing that. It's loading that piece of data. Okay, it's loading the instruction 0100 and the immediate, and you'll notice the accumulator now also has a 5 in it. Notice also that the program counter was incremented from 0 to 1. We now have our arrow pointing at 1. Okay, so now the next instruction 0001 is add. So we had added what was in memory address 4, which was 101000 to the 5, and now this is holding the result of that sum. So you can do 1 step at a time. We're now accessing what is in 2, which is 0101, which is to store. So we're going to now store what's in the accumulator. And where are we going to store it at? Well, we're going to store it in 5, and you'll notice right now we have what is in the accumulator is being stored in 5. The very last instruction, we're now pointing at 3, is 1111, and 1111 is our opcode for stopping. So the program's all done. Now, did you notice that as this was executing, that down here we have our little mnemonic that you see here in the opcode list? So wouldn't it be convenient if you could code like that? And you could. So it was finally decided, probably not too long after people got tired of coding with 1s and 0s, that instead of typing 1111 every time we wanted to stop, let's type STP, and then we'll have a program called an assembler that will convert STP every time to 1111. And that is how assembly language came about. So you will see the instruction followed by the operand. Reset, and if you would like, clear memory, and then you can go and look at subsequent examples. Here is the Lab 8 answer sheet. So you will be, for example, in the first exercise, you will be taking a look at the one we just looked at. And in number 3, I ask you to get that screenshot. And if you recall, I demoed it for Lab 7, but to get the screenshot, I like to use this snipping tool, which comes with Windows, and just get the screenshot and copy that and paste that right into here. I ask you then to go into the opcodes list and decode those first 3 instructions. Remember, each instruction is only the first 4 bits of memory. You will write down load immediate, etc. How many fetch execute cycles will this program run? Well, if it's a sequence, which this one is, it should run as many fetch execute cycles as there are instructions. So I would say there's 4 instructions here. Let's take a look again. So I'm going to load the sequence. 1, 2, 3, 4. There's 4 instructions. So I would say there's 4 fetch execute cycles. So you will step through that for each of the exercises. They do get a little bit more complex. Email me if you have a question on any of them. And try your best, but you are going to do a lot of, well, this instruction means load I, and see if you can, what this is called, disassembling the program and getting the machine code into human readable format. So I hope you enjoy working on this lab.